Well, let's do it. Okay, so to recap, what we did last time was I started with this, I go to this, but I started with this idea of the colorblind friend, which is sort of one of these, we have a litany of cute examples of zero knowledge proofs that we use when we're explaining such things, and this is one of the classics. Um, and that I can somehow convince my friend that I do know how to tell these balls apart, but he can't use that fact to convince anyone else that he can tell the balls apart. And we had this interesting situation where each round of the protocol there was only a 50-50 chance that I wasn't cheating. But of course, if we repeat this enough times, well, then this becomes somehow convincing in a computational sense. And we define a proof of knowledge by, well, I defined, okay, so we have a relation where there are statements and witnesses. There's not a lot of depth to that. And then I defined a proof of knowledge, and a proof of knowledge is supposed to be complete in the normal logic sense, and it's supposed to be sound in this sort of strange computational sense where I say the proof is sound if given rewinding access, or equivalently the ability to rig the probability distribution of my prover, then I can always pull out a witness from a proof that makes a verifier accept. So we have to go over this because this is kind of important. We have PV here, which are specified algorithms, Turing machines, if you like. They are specific algorithms that are the honest version. And then there's also this object P hat, which is something that acts as though it could be P, but maybe it does something different. Maybe it draws from a biased distribution, for example. So that's what we mean by a possibly cheating prover P hat. We're saying that it looks like P, but it might be cheating somehow. It might be following a slightly different protocol that just looks like the real P. Okay, so a proof was sound if we can extract a witness from any prover that makes the verifier accept reliably. And then I gave the example of Schnorr's protocol here, classics. And this is, I mentioned this is the basis of ECDSA signatures, sort of. There's a weird story there, but certainly the basis of EDDSA signatures. And it was a proof of knowledge for a discrete logarithm. And we argued that it was sound because if I look at two transcripts with the same commitments, the commitment being this first step here, then I can always produce a witness. I can just calculate the witness with no problem. And there was sort of this technicality where, well, you know, maybe the prover, if we run it twice, maybe the prover sort of screws up one of the proofs and the verifier doesn't accept it. That's fine, we can just try again. And as long as the prover works with non-negligible probability, then this process will terminate in polynomial time. So that's how we argued soundness. And I'm actually going to start by defining a particular notion based on this. So this idea of running two executions with the same commitment lets us define a very important special class of zero knowledge proofs, and that's what we're going to focus on, at least for today, possibly a little bit next time as well. So let's define this. So a three-move proof of knowledge, three-move being that it has this commitment, challenge, response structure. And we call this property special soundness.
Ruh-roh.
Yeah.
Yeah, the puns on this topic are irresistible.
They really are. What happened to this world?
Yeah, it got smited and broken.
Yeah, so it did.
This represented.
It's been a mess since I've been here.
This was the at the beginning. It was reflected a continuing belief in the possibility of order and truth, and by the end of Gödel's theorem, this dream had been shattered.
Oh, okay.
And here we are.
Very akin to history. That's good.
Okay. So an important idea that I mentioned was that the challenge space which is a subset of the powers of the group, is not in fact the entire set of powers. And this will turn out to be important when we define zero knowledge. So we'll call the challenge space C, curly C, and we'll say proof of knowledge has special soundness if I can do this replay situation. So if we're given two transcripts, TCR and TC prime R prime with different challenges, then we can efficiently compute the witness. So in other words, there's an efficient extractor that can produce the witness from these two transcripts. Okay, so this is special soundness. It's clearly a special case of the more general definition, hence the name. And if you look at the argument that we made last time on this board, essentially we're arguing that if 1 over the size of the challenge space is negligible, then special soundness is good enough, right? We could say that if we have special soundness and the reciprocal of the size of the challenge space is negligible, then we have a sound proof of knowledge. And we are going to revisit this in just a minute. Okay, so I'm going to do one more example of such a 3-move protocol, and not in purple, though purple is a nice color. So this has a pretty wacky name. It is the Guillo-Quisquater protocol, with apologies to the people whose names I butchered. So the idea here is we're going to prove that I know the modular pth root, where p is some prime, of some number. Okay, so the prover sits here, the verifier sits here, and the setup is, so the initial setting is x is in the multiplicative group of integers. I'm trying not to do the cryptographer's abusive notation. So in this the x is in multiplicative group of integers mod m, and we know w such that x equals w to the power of p, and also m and p, of course. The verifier knows x, m, and p. Okay, so the setup is very similar. The first step is that p chooses k uniformly at random. I'm going to introduce this notation. The left arrow with a $sign. This means uniformly at random. The $sign is supposed to make you think of tossing literal coins, right? That's why it's a $sign. I spent a while trying to determine why it was a $sign, and that was the answer I found. And then the prover sets t to be k to the power of p, and sends t to the verifier. Okay, so that's the commitment. The challenge is from a challenge space, which is a subset of the powers, to p minus 1. We'll see why this makes sense in a second. Send back challenge, and now the response is supposed to be is k times w to the c. Send it back, and we accept the proof if r to the power of p equals t times x to the c. So this is almost the same protocol, right? And this is not a coincidence. A lot of these early protocols follow this. This is what we in cryptography sometimes call a sigma protocol. And there's a fun paper by Uli Maurer talking about how all of these are special cases somehow of a general protocol about group homomorphisms. But this is another example. So are there any questions about what's going on here? No? So for completeness, I mean, this is just a calculation. You can do the algebra. So again, we just check that if we expand these two things, we just check that we really do get an equality. Okay, let's go over to the first set. So I'm going to prove special soundness. I'm not going to try to prove full soundness. So we'll assume that the challenge space is big enough, and we're going to prove just special soundness.
Sorry, could you say again what makes soundness stronger? So it's over a broader class of.
Yeah. So special soundness only refers to these three move protocols with the particular structure that I described. Soundness is in definition 3 over on the right. Soundness can refer to any structure of protocol.
Yeah, okay. That's the P
So
hat.
the special, in this case, what's special about it is that it has this 3 move sigma protocol structure.
Okay.
So
would you mind if we
these
leave this board unerased, because I find myself opening it like every 2 minutes to read the definition of the one with the definition of sound on it again.
The last one, yeah.
Yeah.
So we have these two transcripts with different challenges, and they satisfy, because the verifier accepted these transcripts, we have r to the p over r prime to the p equals tx to the c over t x to the c prime, just dividing these two equations, right, that the verifier checked. Remember that for soundness, we assume the verifier is honest, and the prover is the one that we don't trust. And then straightforward calculation, this is x to the c minus c prime, which is equal to, by definition, w to the c minus c prime to the power of p. So we have r over r prime equals, this is in the group, by the way, I'm not writing the mod signs because I'm lazy. So we have this equation, but we also have the equation x equals w to the power of p, and challenges and p are relatively prime. Because p is prime, nothing especially deep there. Incidentally, that's why I don't let the challenges count. You'll note that I said to p minus 1, because if a challenge was p, we would have a problem in this step, right? Not a serious problem, just a weird problem. So I just completely avoid that. Okay. Well, we have relatively prime stuff and some equations. So let's do extended Euclidean algorithm. We find a and b in the integers such that pa plus c minus c prime b equals 1, which means that we have w equals x to the a, r over r prime to the b, just substituting, which is w to the pa times w to the c minus c prime times b. Yes, which is, well, we can just calculate it, right? We can just calculate this.
Isn't that x to the a times r on r prime to the b, not to the power of?
Yes, you are correct. Sorry, my handwriting. Yep. Yep. Okay, and then which is equal to W because we did the Euclidean algorithm, and we can calculate this, and we are done. Okay, so this is just another example of proving special soundness. This one's maybe a slightly more involved. I hope that now you sort of see that we can construct a bunch of such protocols. Any questions at the moment? Great. Okay, so now we know what it means to prove knowledge, at least. Well, we know what it means to know something, and we know what it means to be a proof of knowledge. So let's talk about zero knowledge. Okay, so I will leave the last board up as per Dan's request. So we learned how to define knowing something, right? And now we're going to learn how to define not knowing something, which is not the opposite, right? In particular, we're going to define what it means to not learn something. Okay, so the idea is that when you witness this protocol, right, when you participate in this protocol, you actually don't learn anything other than the fact that the prover knows the witness, okay? So if you watched any of the UC seminars, this will sound a bit familiar. Our idea is to show that the verifier could have simulated the entire interaction with the prover. Okay, so in this setting, we assume that the prover is honest now, and the verifier might be doing something dodgy. And the idea is we're going to show that the verifier could participate in the protocol with P, but the verifier could also produce a transcript that looks like it participated with P all along, right? And that means that it can't have learned anything because it could have just simulated it anyway. So when it interacted with the real P, well, it can't possibly have learned anything. It could have just simulated it on its own. So the only thing that the verifier gets out of interacting with the prover, if this property is satisfied, is that P knows the witness. That's the only thing that they'll learn. Okay, so we want a technical gadget first. And we'll take a protocol PV. And we define the view of a verifier. And again, we're assuming that the verifier might be cheating. So we look at V hat, which means it looks like V, but maybe it's not actually drawing things uniformly at random like it's supposed to. And we'll write this in a not very shocking way as view sub P of V hat, meaning the view of V hat interacting with P. And this thing is the random tape of V hat. So the randomness, in other words, wherever it's drawing randomness from, we'll include that in the view. And we'll also include the public messages, the transcript between P and V. Okay. I guess technically, really, I mean to say for protocol execution in some sense, right? So the view of V hat in some execution of the protocol, and of course that means that this is a distribution overviews, really. I'm abusing notation a little bit, sorry. For cryptographers, we do that. Okay, so if we've got a view, well, let's define the zero knowledge. Okay, so a protocol.
I don't follow this definition, sorry.
Yeah, go on, Dan.
So I understand what it means to have an execution of this protocol, but where does V hat sit in the protocol? I don't know what it means to...
So, right, I realize now that this notation is starting to get very hand wavy. What I mean by this is P and V hat interacting produces what's the right notation for this? It somehow produces a random variable that's drawn from this distribution, right?
Yeah, that part doesn't disturb me.
Did that make sense?
Yeah, but so what you're saying is you put v hat in place of v, you get some trace of execution, and you also include in this data structure called the view what the real v would have done. Is that right?
No. You include v hat's randomness. Okay, so if v hat equals v, if we're looking at the honest verifier, then somehow to know that it's honest, it has to have chosen its challenge uniformly randomly. So we have to know what its random tape was to check that it was actually generating the challenge uniformly at random. Right? So we're including.
I see.
Yeah, we're assuming you know the strategy somehow, or in other words, you know v hat as a Turing machine. You chuck in the random tape as well, so that you, the mathematician floating in the ether, can run v hat and verify that it's going to generate the transcript.
Okay, yeah, that fits very well with the earlier definition. Sure, okay, I understand.
Right.
I'm still a little confused.
Yeah, go on, Matt.
You said you can run, the mathematician in the ether can run v hat. Do you mean they could run v and see if they get the same transcript?
Either. So the mathematician in the ether knows P and V, which are the honest protocol Turing machines that are supposed to do it. And if we fix some v hat, then we say, well, if the mathematician knows v hat and it knows v hat's randomness tape, it can see what v hat would do given the commitment T.
Okay.
Right? So that's why we include the random tape.
Okay. And the random tape is basically like a seed in
yeah. So the picture is, imagine an infinitely long tape full of uniformly distributed zeros and ones, which of course doesn't exist. But
but whenever it needs
and whenever the Turing machine exactly just pulls a coin out of that random tape. This is actually sort of one of the awkward points of crypto, that of course no actual infinite uniform distribution exists. So we sort of hand wave and say, well, you have an upper bound on the runtime, so make it big enough, something like that. Yeah, dev random, exactly.
Is this v or v hat here with the green arrow?
That's v hat.
Yeah. Okay.
I shall ensure that this is clearer.
Yeah, that was the main thing that confused me, the presence of both of them.
Okay.
Yeah, I understand that. Yeah.
Okay, we good now?
Yep.
Fantastic. Okay, so I will define the protocol to be perfect zero knowledge. Foreshadowing, there is such a thing as imperfect zero knowledge. If for all possibly dishonest verifiers v hat, one of the crypto abuses of notation is creeping in. We mean probabilistic polynomial time. Right. When we're talking about a verify, it has to be efficient, so it's probabilistic polynomial time. That's just hidden in there. This is sort of the crypto culture. So for all possibly dishonest efficient verifiers, there exists an efficient simulator. The efficient part is really important here. An efficient simulator, which is another algorithm. I write this in red because the name. And we'll call it S, such that the distribution, right? We're thinking of the view as a distribution over randomness tapes. Is equal, hence perfect zero knowledge, equal to the output distribution of S. So that's perfect zero knowledge. The idea is that there is a simulator that has to be efficient. The efficient part is really crucial, such that the distributions of v hat interacting with the prover and whatever the simulator spits out are equal. They're exactly the same. The simulator can just run the protocol. Okay, so, and of course the simulator is, look at the order of the quantifiers, right? The simulator is defined in terms of the verifiers. So the simulator knows what the verifier is. That's intended. And if instead the distributions are computationally indistinguishable, I'll get into what that means in just a second. If they're computationally indistinguishable, we just say that the protocol is computational zero knowledge. Or, because we love abusing terminology, we often just call this zero knowledge. ZK for zero knowledge. Okay, so computationally indistinguishable is this phrase that pops up all over crypto. And the idea is that there exists no efficient Turing machine that can tell apart the distributions with more than negligible probability. So in other words, to a computer, the two distributions look basically the same. Does that make sense? To an efficient computer. Questions?
Which would mean there's no like predictable way in which they systematically differ.
Right. The only way you can tell them apart is if you get really lucky somehow.
Mm-hmm.
Like there's a very unlikely event where you can go, oh, the distributions disagree. That almost never happens. So remember, negligible was this thing I defined last time. Mm-hmm. It's just, it decays faster than any polynomial, 1 over any polynomial. Happy?
Maybe.
So, I mean, do we understand this definition on the nose? Perhaps the interpretation is not clear, but do we understand what it actually just says so far? You're essentially asking the simulator to produce a fake view in an efficient way.
Yeah, I think I got that. I'm missing something. And I think it's this whole slide. Simulating the interaction with P is meant to show that V doesn't have some information, but I've got two things that aren't coming together in my head. One of them is that I'm not sure what S is missing. Why is it impressive that it can simulate V? And I'm not sure what couldn't.
Sorry. It actually, you should think of it as simulating P, not V.
Okay. Yeah, so because it's missing P. Like we're giving it. Yeah.
Right. The picture is the verifier runs the simulator in order to produce an interaction that looks like something the prover would have said. And if the transcript distribution, the view distribution of the simulator is equal to the view distribution it would get by interacting with the prover, well, then you have no way to tell these apart, right? So in other words, they are exactly the same thing. Did that make sense? Maybe the first thing I want to make sure is that we understand this definition on the nose, right? Interpretation is tricky, that's true. But do we get what it's actually literally saying?
Yes.
Cool. Okay. So it's instructive to look at an example, right? So I'm going to prove to you, sort of. I'm going to cheat a little bit, but I'm going to do what looks like proving that Schnorr's protocol is zero knowledge. Okay. So we have our commitment T, which is G to the power of K for some random K. We have our challenge, which was chosen uniformly at random from C. and we have our response, which is K plus WC. And our goal is to produce a distribution of TCRs that is identical to the real protocol. So we don't know X, okay? We don't know W, we don't know witness. We just want to produce a bunch of TCRs that look like the TCRs that I defined there that go in the protocol. So, well, how are we going to do this? We want to satisfy G to the R equals Tx to the C, right? Well, to satisfy this equation, what would we do? Any ideas? We know G and we know X, they're fixed, and we can choose TCR however we like. Any ideas? Just say the obvious. This is obvious somehow.
Can you state the problem again, please?
Yeah. So the real protocol, we had the first step, commitment T, second step, challenge C, third step, compute R. Now our goal is simply to produce a TCR that satisfies this equation, and then we'll check whether it looks like the real distribution. So all we want to do right now is to make up a TCR that satisfies this. We can do it however we want, as long as it's efficient.
I don't get what's fixed. So X and G are fixed, right?
Yep, X and G are fixed. T and C are free.
So you're just going to make T G on X and then R equals C equals 1.
Yeah, exactly. Well, yeah, okay, that's a good start. That certainly works. But that's obviously not going to match the transcript distribution, right? T, C, and R have to look random, right?
I thought you said we can choose them to be whatever we want.
Yeah, but our bigger picture goal is to match the distribution of these that we would get from the Schnorr protocol, right?
Right.
So if we just fix R and C to be a specific value, then it satisfies the equation, but it doesn't really do the job. So the first thing we're going to do, yeah, Matt, go ahead.
I was going to suggest just like picking some W and then pretending that's the W and simulating what the prover would do. I forgot what K is, but
X and K is chosen at random. So the problem with this is that X and G are fixed, and W is a relationship between X and G, right? So you can't just pick any W because that would not work. So the idea, and this idea appears again and again, is we're just going to run the protocol backwards, right? The protocol started by choosing a commitment and ended by choosing a response. We're going to choose a response and then compute the commitment that makes it work. Okay, we do it backwards. And if we do it backwards, it's easy. The only reason the prover can't cheat is because it's going forwards. If the prover was allowed to go backwards, it would be super easy, right?
Right.
So
because that's the point, is the challenge has to come after the commitment.
After the commitment, exactly.
Right, but if you don't have to pre-commit, then that makes intuitive sense. Although I'm not really, I'll flag that I'm not really following the specifics of the equations here in general.
Sure,
but that's okay.
The details are on the board at the back. The algebra is worked out on the second board. You see that it works out if you do the algebra.
Yeah.
So we're going to do it backwards. We choose our response. And we can actually choose in some cases, you might want to now compute a particular challenge, but we're just going to choose it at random. That's good enough. and we choose it from our challenger space C. And then for a t, we just compute the t that works. So this works out to be g to the r, x to the minus c. Okay, and then, well, okay, you see the equation is immediately satisfied, right? So we have produced a TCR that certainly satisfies the equation. Does it match the distribution? Well, R and C, if you look at the real protocol, C is uniformly random, tick. And T is G to the power, oh, sorry, I did this backwards. R is a uniformly random thing plus W times a uniformly random thing. So R is uniformly random, right? The distribution of R is uniform. Do you agree with that? Sort of this classic trick in crypto, right? Where you add, if you multiply a uniformly random thing by anything, the result is still uniformly random, unless it's zero, of course. If you add two uniformly random things, you still have a uniformly random thing, okay? So the response
If you add,
also is random in the real protocol. Matt, yeah?
If you add if you add k to something that's not uniformly random, then what? Wouldn't that also be?
Probably. I didn't think about it when I was preparing today.
Okay.
But you can do the idea is you can do a bunch of stuff and then it still turns out to be uniformly random.
Yes.
Okay. Yeah. In the real protocol, well, T is uniformly random because it's G to a random power. And we did it, right? We simulated the protocol. Do you agree?
We definitely reckon the product of two random numbers is uniformly random, which is what you were going to say, right?
Yeah.
Well,
thanks.
Sure. Fantastic. Okay, so we did it, right? Did we simulate the protocol? Did we produce our efficient simulator?
You told us you were going to cheat a little bit.
Yeah, I cheated. What did I cheat on? In what way did I cheat?
On that.
One of these three steps is dubious.
So, this is probably wrong, but if you looked at this simulator and you looked at, would you be able to extract a consistent W from it, and maybe you'd be able to tell, or something? I think probably no, because of all the uniformly random stuff that was going on.
Right. There's no way to efficiently extract a witness from the simulator, but it's a good guess. The problem is specifically here. Is that a big enough hint or not? Yeah, so the verifier chooses the challenge uniformly at random. Does it though? Remember that we have to define a simulator for any verifier, not just the honest verifier.
Okay. Yeah, that makes sense.
So what about a cheating verifier?
Mm-hmm. We have its random tape. So we could do what it will do, but we'll have to also check that that doesn't give us away.
So you're saying, here's the problem, right? So give us away, yeah. So we could absolutely, with no problem, if the verifier is choosing C according to some non-uniform random distribution, then we could still choose C the same way as the cheating verifier, right? That would be no problem.
Well, as far as choosing C goes, it would be no problem.
Right. But here's the thing, the cheating verifier may not be choosing C from a random distribution. It might be computing something from the commitment, right?
Okay, yeah.
Yeah, so if the verifier is cheating, then you can't just draw C from a random distribution and expect it to match what the cheating verifier is doing. So we only prove that this only works for honest verifiers. But all is not lost. There is a way that we could try to make it work for dishonest verifiers. The argument goes like this. We do just choose our challenge uniformly at random. Now we compute T according to whatever rule, in this case, step 3 above. And now we check if V hat would have responded to T with C. Okay, so we just guess and we see if we're right. And if not, try again. No, go back to R. Go back to 1. Just try again.
Okay. Is this where it's going to become important that we had a limited challenge set?
That's why it's important that we have. Why is it important that we had a limited challenge set, Matt?
This could be This could be a hopeless exercise if you didn't have some constraints on the possible challenges.
Yeah. In particular, it turns out that we need challenge space to be polynomial in size.
Of course.
Polynomially bounded. This is a problem, right? Because if it's polynomially bounded, well, it's not sound anymore. So we could just give up here and say, well, it's doomed. You can't have a 3-move protocol like this be both perfect zero knowledge, at least, and also sound. We somehow we could say, oh, we can't do it. Oh well, very sad. But actually, we can do it, and the trick is not that complicated. In fact, it's exactly the same as the colorblind friend, right? We had a very small challenge space. The challenge space was either swap the balls or don't swap the balls. It's only 2 things. But then we just did it a bunch of times, and we say, well, the soundness error gets very small very quickly. So we can do exactly the same thing here, and we can use this to reduce both soundness and zero knowledgeness. The idea is that we take this 3-move protocol and we repeat the 3-move rounds several times. If we do it enough times, we'll end up with a negligible soundness error while still being zero knowledge in each round. Let's see. I'll start sketching out how this works. I won't get to finish it, but we'll start with it.
Cool.
I'll leave up Schnorr's protocol just for concreteness. So theorem, we got there. A protocol. First, I'm going to prove that even if the challenge space is polynomially bounded, we still get a proof of knowledge. We still get soundness. So, protocol PV consisting of S special sound rounds is a proof of knowledge. In other words, this means it is sound. As long as 1 over the size of the challenge space to the power of S is negligible. Okay, so even if the challenge space is very small, if we do it enough times, we still get a proof of knowledge. Of course, S is allowed to depend on the size of the challenge space, right? As an aside, the way that you should be thinking about this, and this is something that is often not explicitly said in crypto texts, the idea is that we have a security parameter, call it lambda by convention, and the challenge space, in particular the size of the challenge space, is a function of lambda. And also S is a function of lambda. Okay, so this is how we arrive at 1 over the size of the challenge space to the power of S is negligible, right? They're both functions of some parameter lambda, and that's the that would be the parameter of the polynomial we are comparing it to make sure it vanishes faster. A lot of crypto is written pretty vaguely. It's like, oh yeah, it's negligible. Negligible means what exactly? It means something like that. Okay.
Yeah.
So, proof. I did promise at some point we would prove some theorems. So to prove this, we have to produce an extractor that does what it's supposed to. So we're going to construct our extractor E as follows. The first thing it does is it fixes p hat's randomness. So we're proving soundness, so we have a possibly cheating prover, and we have rewinding access so we can rig its random tape however we want. Now we're going to run parallel executions between p hat and the honest verifier, where V's randomness is different. Okay, so p hat has the same randomness in both universes, but V has different randomness. Now we have a sequence of transcripts. We have sequences of transcripts, T1, C1, R1, ... up to TS, CS, RS. And we also have the other universe's transcripts, T1, not prime because P's randomness is fixed, C1 prime because R's randomness is not fixed, and R1 prime up to TS, CS prime, RS prime. So what we're going to do is we find round I such that Ci is not equal to Ci prime. So we're going to just go through the rounds one by one, find the first round with different challenges. But of course the same commitments. And we're going to use special soundness to compute our witness. Okay, so we just find the first round where we have this special soundness hypothesis, and then we just pull the witness out. Now, it's possible that we are very unlucky, and in fact, V ends up always choosing the same challenge, right? That's possible, that we actually end up with the same challenges in every single round, but it can't happen that often, okay? In particular, since 1 over C to the S is negligible, the probability of any particular sequence from T1, C1, R1, TS, CS, RS is negligible, right? Because the size of this thing Well, it's 1 over. It's at least the size of the child in space to the power of s. So the chance of picking any one of these is negligible. Therefore, he succeeds in at most polynomially many attempts on average. And if you recall, we only required it to work in polynomial time in expectation. Done. So the picture really is quite simple. We're doing the protocol in 2 parallel universes. At some point, the challenges with overwhelming probability will differ, and then we can use special soundness to extract the witness. So we have soundness. Questions? Sure.
I think it's good.
Matt?
I think it's good. I like it.
Right, okay. That's the end of the sentence.
Yeah.
So, this proof crucially relied on the fact that the verifier was honest, right? If the verifier wasn't honest, then we couldn't use this trick where we say the challenges will eventually differ, because the verifier might be screwing with us and always outputting the same challenges. But because the verifier is honest, there's no way that we can get so unlucky that we never find a round that we can extract our witness from.
Yeah.
Yeah. Yeah. Dan, did you finish? Do you still need time to think about it? Sure, yeah. I should be clear that I haven't very ability for what I'm presenting for 2 reasons. First, I trust Uli, who wrote the paper that I'm plucking this proof from, which I'll chuck in the Discord if it isn't already. And 2, because I'm not very good at probability. But yeah, this proof is, I believe, fairly watertight. The result that we were going to do next time about zero knowledge is a little trickier. What we're going to do is we're going to prove that if we do S rounds where we have this honest verifier property that I mentioned before, where the challenge size and S are polynomially bounded, we'll get perfect zero knowledge. And then the idea is, okay, so I can choose C and S to make sure that this hypothesis in blue is satisfied. But because they're both polynomials, if I do S rounds where the challenge space is also a polynomial, then I just multiply 2 polynomials, so I stay polynomial. That's the idea. So in other words, that's how we're going to conclude that the simulator stays efficient. And the punchline is that if you do Schnorr's protocol a bunch of times, then you have a zero knowledge proof of knowledge, which you could apply in great generality. In fact, people do. Okay, any last questions before we close it off?
Yeah, I do have a question.
Matt, yeah?
I'm missing something. The simulator definition of zero knowledge, I'm not getting that, because it seems like, for example, if you were to, someone is like displaying zero knowledge if you can simulate them without the knowledge, but it's not clear to me that they don't have the knowledge or something like that. I don't know if that
makes sense. Yeah. The crucial point, I tried to label this, but I guess I didn't make it clear enough. The crucial point is we're not arguing whether the verifier knows the witness. We are arguing whether the verifier could learn the witness by interacting with the prover. It's possible that the verifier does the protocol with the prover, even though it already knows the witness, right?
So it's not about the verifier. It's about the proof. It's about the prover. I think you said that earlier. Yeah, that's making more sense now.
About the prover in what sense?
Like you, it's about it made sense in my head.
Yeah, I know it's tricky. My view on it is because of soundness, the prover must know the witness. Because of zero knowledge, the verifier couldn't have learned the witness by interacting with the prover.
Yes.
Right. That's why I say learned. Right. We're not arguing that it doesn't know the witness. We're arguing that it didn't. It's not that it doesn't have the knowledge. It's that it couldn't get the knowledge from the protocol.
Yeah, that's right. It's like someone who didn't have the knowledge wouldn't now have the knowledge based on these interactions.
Right. Exactly.
That makes sense. Yeah. Got it.
Yeah. And yeah, this is actually a brief comment is that this is what attracted me to crypto in the first place. This definition is really strange, but if you carefully think through, you realize it makes sense. Not only does it make sense, it's extremely powerful, and that's really, yeah, that's what got me into crypto. So I hope you're all enjoying learning about zero knowledge proofs as much as I am.